Hi guys, this is Dan Bentley from Section D. I have a few questions that I am going to look at from Paper 1, Section A from your exam. Just look at it in a little more depth and how they were assigned points. I think we're going to look at questions 2, 4, and 7 were the ones I were going to highlight with you. These were ones that as I was looking at my section, there were some little difficulties that I wanted to sort of shed some light on. The first question is completing the square, and I think most of us are pretty good at completing the square at this point, but there's a common mistake happens in completing the square. First, we take that middle term and we half it and then square it to get that term, that third term to complete the perfect trinomial, and in this case it was 4. And I also need to subtract the 4 because that would just be adding 0 to something. Now that these three terms make up my binomial squared, but here's where the error usually happens, is that on the next step here, a lot of people forget to distribute this 2 to that negative 4 there, so you get negative 8. So sometimes if that was missed, that led you to a wrong vertex. So our final, in vertex form, is our final function is f at x equals 2x minus 2 quantity squared minus 3, and our vertex is looking right at us with the positive 2 and the negative 3. This was a bit tricky, moving it. It looked like a simple question, but there was one piece. You have these two graphs, so you realize you've put it in vertex form, and that's where your original graph is, and it needs to be moved to x squared plus 4. So a lot of people wanted to move it up 7, directly up 7, because it's going from negative 3 up 7. And actually, I did too when I first looked at this question. But then you realize you have to get it back to the x-axis, so you have to shift it up 3. Now you apply the stretch factor of 1/2 to it. If you apply that stretch factor first, you will actually be shifting your stretch, or stretching your shift. So that's why it's important that you do this intermediate step. Once you get it onto the x-axis and you use that stretch factor, then you can move it to the left 2, and then up 4 units to get it to our final answer of x squared plus 4. Okay, and you were given some, I think, A1 point for two A1 points for this question. Okay. The next question, question 4, I'm going to talk about, we needed to come up with the equation for f, and you looked and you saw your zeros were at 3 and 0. But at 0 also recognize that it's a double 0, it just touches the axes there. There's a double root. So we know that our factors would be x minus 3 and x minus 0 squared. Okay, so if I'm writing that in equation form, it might look something like x squared minus 3. But if you notice, I put an a there, because there could possibly be a constant other than 1 in front of that x squared. I mean, this is going to determine how deep this graph goes for its max and mins. So we've also given you some information about a point that lies on the graph, which is 2, negative 8. So I just am going to plug in for x 2 and for y negative 8. And then I'm going to solve that through for a and get that constant multiplier. And I think that you will get an a, let's work this through here, an a of 2. And then you roll that back into your equation or your function. I should be writing this in function notation because it did ask for f. And you can leave it in factored form, or it was fine as well to distribute it through and get 2x cubed minus 6x squared. And you were given a method point and an answer point for getting recognizing that you needed the constant. You were given a method point for working through plugging in 2 and negative 8 and for working that through, and then an answer point for bringing it all together at the end. We were then asked with this graph to graph f absolute value of x. So if I think about this graph, and I can draw the right half of it here. This is the right half of the graph. But then this is actually just sort of a reflection over the y-axis. And if you think about why this happens, let's just pick a point. Let's say x equals 1. What's f at x? Well, if x equals 1, we'd plug it into that equation on that last slide there, and you would get 1, negative 4. Okay, now imagine we were to plug in negative 1. Well, as soon as we plug in negative 1, the absolute value is taken on the negative 1, and it is simply just turned into a positive. And then so I'm really working with a positive one, so I'll get the exact same answer for f at x. And you are awarded points by getting those intercepts correct and also the general shape of the graph there. The last question I want to talk is here, question 7. We'll talk about this. And this was actually what I like to call a quadratic in disguise. At first it looks pretty tough to solve, but if you multiply both sides of this by e to the x, you end up getting something that looks like this. And you might say, I don't see a quadratic there. Well, what if you let e to the x equal u? And all of a sudden you get a nice quadratic, which is actually which is very easily factorable. And then you can just open up the u and say, oh, it wasn't actually u, it was e to the x equals -3, or e to the x equals 2. And then maybe as you look at each of these solutions, you remember e to the x is actually never positive, so I can cancel that solution out. And then I can continue here with natural log of e to the x. I'm taking the natural log of both sides. I need to continue to solve for x because the question asked me to solve. I took the natural log of both sides, and that gives me x equals the natural log of 2. And the b part of this question was working with logs again, and I needed to get log base 8 of 5 equals k, and get that in terms of log, and solve log base 2 of 20 in terms of k. So I'm going to work with this log base 8 of 5, and I'm going to use the change of base formula because then I can pick whatever base I want, and I'm going to pick a base 2. It makes sense because that's what I need to get my answer in terms of in the end. So if I go log base 2 of 5 and log base 2 of 8, then that denominator is just simply 3, and then I can just cross multiply this, and I can say log base 2 of 5 equals 3k. But let's look at this other side. Let's look at log base 2 of 20. I can use my logarithmic laws, and I can kind of bust this up into a sum. And the great part is I have log base 2 of 5. I know that that's 3k, and log base 2 of 4 is simply just 2. So now I have rewritten my log base 2 of 20 in terms of k. And we'll give you a method point there for using the change of base formula, an answer point for getting 3k, another method point for for breaking up that logarithm, and then for bringing it all together with 3k plus 2 is your last answer point there. Okay, well, that's all I have for you. Please make sure you look at the mark scheme to check out your other questions, and the other teachers will be posting some videos as well to give you more details on some of the questions in the others parts. I hope you have a great holiday, and take care. We'll talk to you again.